morning, everybody, and welcome to our bright and early Tasmanian time fourth session. And good evening to those for whom it is evening, and good afternoon to the rest of you, I suppose. This is our network session, so I'm very happy to introduce Hector Baños as our first speaker. He's going to speak about joint work with John Rhodes and Elizabeth Allman. Thanks, Hector.
Okay, can you see my slides?
Yes, we can.
Great. Okay, so I'm gonna start. So hello, my name is Hector. Right now I am a postdoc at Georgia Tech, and what I'm gonna be talking about is joint work with Elizabeth Allman and John Rhodes, both which are in the University of Alaska Fairbanks. Okay. So more evidence is now available showing that hybridization has played an important role in evolution. And what you can see there is just a cartoon of what do I mean by hybridization. And that is when two different species merge genetically to create a new one, like Kermit and Miss Piggy will create a new species. And although this is a cartoon, that is shown that is true for fish, frogs, and plants, and salamanders and other species that are showing more traces of hybridization. So on the background model that we work on is the network multispecies coalescent model, and some talks have really beautifully introduced the coalescent model. The one we're working is a generalization by Kubako and Meng that accounts for hybridization. And I'm going to give just a really brief explanation of what it is. So we have a species network, well, you can see here. Each tube represents a population. And you can see these lines, those represent generations. So we measure time going from present to past, and this is the number of generations. I'm showing a discrete picture of it, even though it's a continuous process, but it's easier to see it as a discrete, to explain it. Now, in each these generations, you can see little dots. Those represent individuals. So this is relating the species A, B, C, and D. And here, for example, we have two hybrid edges or two hybrid populations where they match genetically to create a new one. And for each hybridization event, we have a parameter gamma that I'm going to explain what it is a little bit later. And here we can think about this is the population of Kermit the Frog, the population of Miss Piggy, and they joined to create the new little pink frog that we see. So the way it works is that you sample a lineage per species, and then you trace back its ancestry via a Poisson model, and then there could be several things happening. Sometimes when you have two lineages in the same population and then trace back to the same ancestry, we call that a coalescent event. Okay. So, and then you keep going in the process just with one less lineage, and until the point where you have only one lineage left. You go always back in time. Now, the difference between the multispecies coalescent model and the network multispecies coalescent model is that when you have a hybridization event, this lineage will trace back its ancestry with probability gamma, this edge, and with probability 1 minus gamma, that edge. So it could be that both these lineages that are present at this time will trace their ancestry back to this population with probability gamma squared, or 1 minus gamma squared if both go this way, or probability gamma times gamma squared if this one goes this way and this one goes that way. So really the network multispecies coalescent model describes this as stochastic model of gene tree generation. So what we see here is how we can sample a gene tree from a given species network. Okay, so that is the model we're thinking about in terms of gene tree generation. Why we like the network multispecies coalescent model? Because it accounts for incomplete lineage sorting and hybridization. Now, for the sequence substitution models on gene trees, we assume there's a general time reversible model, GTR. Most of you may be familiar, which is a continuous time Markov process on a metric gene tree. We have the gene tree, of course, and two parameters, Q and pi. Q is a 4x4 rate matrix. Pi is the root distribution, which tells you the proportion of adenine A, G's, and T's, C's and T's, respectively. And then on each edge of our gene tree, we'll define a Markov matrix ME, which is the exponential of the rate matrix times the length of such edge. So this edge has length TE, therefore this is the Markov matrix. So the way that we can sample the sequences is we just sample a nucleotide with this distribution at the root. Then once we sample, we have a given probability of switching to some other state. And because we have a Markov matrix for each edge, we'll have these switches. Okay, so now the model that we work on is the mixture of coalescent mixtures. And it's just a three-step process. So we assume we have an ultrametric species network, and ultrametric in the sense is there's the same distance from the root to any of the lineages in any given path. And as mentioned, we can sample a gene tree from that under the network multi-species coalescent model. So we sample it. Then we select parameters Qi and Pi from a finite list. So we have a list of sets of parameters, a matrix Q and a distribution Pi, and we will sample one at random. And then once we have our sample tree and our sample parameters, we generate sequences as described under the GTR process, that's our step 3. Okay, so the question we're interested in is, given genomic DNA sequences sampled from, mixture of coalescent mixtures, what properties can we identify from the network? Someone handed us these things that we're generating on our model M, or mixture of coalescent mixtures. What can we tell about the network? So for our identifiability result, we use the log-dead distance, which again, most of you may be familiar. I'm gonna briefly explain. So the log-dead distance is the distance between two sequences, is defined by this equation where we need two things, FAB, that is just the side pattern frequency matrix of two sequences. And the way we define it is you have the two sequences, rows will correspond to, let's say, A, columns will correspond to sequence B. And then each entry, for example, this entry represents the proportion of sites where you see a G in A and a C in B. Of those two have length 15, and in two of these places, we see a GC, a G in A and a C in B. So that is the frequency is 2/15. That is this matrix that we have to take the determinant and then the logarithm of that. And then we have two numbers, GA and GB, which are the product of the marginals of the frequent pattern side frequency matrix, which is just when you add all, just represents the proportion of A's, adenines in A, the proportion of G's in A, etc., etc. The product of those entries of the row marginalization and column marginalization will be GA and GB respectively. Okay, so the log-dead distance was introduced to consistently infer gene trees for one GTR model. This was done by Lockhart, Steele, Handy and Penny in '94. And then Allman, Long, and Rhodes showed a species tree identifiability under the mixture of coalescent mixtures, or the model M. Now, this result, if we were like having a beer or we were in a bar just chatting about, that is something that it seems quite like it's hard to believe just by talking about, because you have this gene tree generation and then you have the GTR model, and then you concatenate all those gene trees, and then can you infer? That was something I was not. It was hard for me to believe until they got it. And the key of their proof is the fact that on the model M, on this tree, the distance between the log-dead distance between BC and AC is equal and greater than the distance between A and B, which again, in terms of a tree, like metric tree, you can always think about, oh yeah, that makes sense. But the problem again is we have all the noise from the coalescent and then the different GTR models. So that was not, that is not trivial at all. And why I'm focusing, why I'm telling about their approach to their proof is because we did something similar, which let me first introduce what's a triple network. So suppose we have a species network, which this is like the ones with the tubes, but I just draw it as skinny for simplicity, but this is like each edge represents population. Then this triple network, you take any three taxa, and then you take all the paths from the root to those taxa, all different paths, and then you suppress degree to nodes, and then if you get something that is hybrid and non-hybrid, you make that hybrid. So the induced triple network of Aijk in this species network is that one. Now, because the class of all phylogenetic networks is often too large to say something really strong, we will just focus on level 1 networks, which we say a network is level 1 if no pairs of cycles in N share an edge. So in this picture, we see this is a level 1 network because this cycle does not share any edge with any other cycle, and the same for all others. But this one is not level 1 because, for example, this cycle share an edge with this cycle. The level 1 condition may feel strong, but I don't think it's that strong. And we're also working on going beyond level 1 networks. So that is something that is being worked. But for now, I'm going to present of level 1. The definition of level 1 may not agree with that of the in the talk of Vincent, but that is just because we're working on binary networks. We can there's a result of Rosello and Valiente where those definitions are the same. Okay, so what can we see in level 1 triple networks? So there's in a triple network that is level 1, there could be cycles of almost size 4 in 8. What is a cycle of size 4 is just look at how many edges that cycle it has. They don't have to be directed. So these are cycles of size 4. You can have cycles of size 3, like these ones. You can have cycles of size 2. You can have multiple, like you can have cycles of size 3 and size 2 and different combinations. Some of them are not, like you cannot have a cycle of size 4 and a size 3 in that same network if it's level 1. But you can have 4 cycles and 2 cycles. And these are all the cycles up to relabeling of the taxa. So what we did is you take, given a triple network, you take all the pairwise locked distances. And that gives you a triplet, like the distance between AB, AC, and BC. And then when you normalize that, you divide over the sum of those entries, you get a point in the probability simplex. The probability simplex is that it's a set of points in R3 which satisfies that the entries are non-negative and they add to 1. And when you look at for above, it looks like a triangle. Like that is what happens when you look at from above. So what we were able to show is that if you have a 4 cycle in your triplet, it doesn't matter who is the hybrid edge. If you have a 4 cycle, it will lie in any of these colored regions, excluding these lines in the middle. Okay. Moreover, depending on the order of the taxa, you will know in which region of the simplex they will lie. For example, for all these 3 triple networks with 4 cycles, you can see that the order always A is in the middle, right? So for these networks, the triple, the normalized triplet of log distances will lie in this region where A is the one in the middle, independently of who is the hybrid node. If we switch them in any of these networks, which switch B and A, then that point will lie on this plum region.
Sound all right? Yeah.
Okay. So we also show that if you do not have a force cycle, then that triplet, that normalized triplet, will lie in these lines, the ones that generically they will lie in these lines that are the ones excluded from here, generically speaking. So moreover, the underlying topology of the network, you can tell depending on which line of the simplex they lie, you can tell the underlying topology. So what I mean by this is something like in the talk of Katerina, where she was talking about displaying trees. This is the same. If you have no force cycles, then it doesn't matter which edge you take, the underlying topology will be the same. So what I'm saying here is that the ordering of log distances on a triplet yields some information about the induced triple network. And just what I want to say is, for example, if we have this triple network, right, that does not have a force cycle, it have a 3 cycle and 2 cycle, what I can tell is the underlying topology, that it looks like this. If I have a force cycle, like this one, maybe I have something else, but if I have a force cycle where A is the node in the middle, then I know the underlying topology only for log distances. Now, we are losing who is the hybrid node and the cycles, but that is okay for now. So what we have done for now is for each triplet, we know either there's a big hybridization or a hybridization involving for a species, or there's no hybridization involving for a species, all species in the triplet. So what we do is we use a combinatorial argument that combines the information of all triplets to recover most of the features of N. So if you know for any given a species network, if you know the information for each triplet, whether it's something like this or something like that, we have the following. Under the mixture of coalescent mixtures, model M on a ultrametric species network, most of the species network topology is identifiable from log distances. And what do I mean by most? Suppose this is the species network, and then under the mixture of coalescent mixtures, you generate the sequences. Using log distances, we can recover this network. And this network is almost this network, but we lose cycles of size 2. Those ones are lost. Cycles of size 3, like this one, is lost too. And on cycles of size 4, we don't know which one is the hybrid node. Here it was G, but in this case, we're not able to tell. Now, small cycles, I am not that bummed out that we lose them, because in terms of the competing signals in hybridization, they don't tell you a lot. Like, it's just a speciation event and then hybridization. So those ones, that is okay, like we can lose them. Same for some three cycles of size 3, like these ones, J and K will eventually join either sooner or later, and that is what this means. We get bigger cycles, and we actually can tell which nodes are the hybrid nodes of big cycles, and those are the ones that have more competing signals in terms of the I, whether it will, these two species hybridize to get I, that it has some relationships with these tags. And in terms of force cycles, yeah, that is, we cannot, for now, we cannot get which one is the hybrid in this particular case. Now, the proof of such algorithm involves a couple of processes. So the first part was to identify the where in the simplex these points will lie, and that had involved like some conditioning on the coalescent process, because we have a network and then we write that network as a linear combination of coalescent processes on the underlying trees, but up to some conditioning if whether a coalescent event has occurred before or after the hybridization. And then once we get that, we use the combinatorial argument to use all the triplet information to put it together to get the network. So that is the main result in terms of identifiability. Now, in terms of practicality of the method, I'm going to talk about some other algorithm that it does not seem to fit here, but I explain why a little bit later. So I'm going to talk a little bit about Nanook. The Nanook algorithm for inference, it's an algorithm to infer a topological species network. It stands for Network Inference Algorithm via NeighborNet using quartet distance. So the input of such algorithm is gene trees that if they have been generated under the network multi-species coalescent model on a level 1 network, the output will be an unrooted semi-directed network that know some of the hybridizations. More precisely, if you generated gene trees under this network and you feed it to Nanook, you will get the unrooted version of that network. So how does Nanook work? So you feed the gene trees, and then in this arrow, there's some hidden processes, but then what we construct is a matrix, taxon, intertaxon, the similarity matrix between taxa. And then once we obtain that, we use splits tree. Formally, we use NeighborNet and the circular split algorithm to construct a splits graph. Now, under the theory that we have developed, the type of splits graph that we'll see, it's special, and we call them dark networks, which we have some terms on how you can interpret biologically what does the signals mean in terms of these. So we have some terms to be able to interpret those dark networks as to get the information about the network, the splits graph, sorry, to get information about the networks. So, okay, so dark networks, I just wanted to add a little bit more picture about how they look like these are actually generated using the splits tree, and this is the type of things, and you can see there's a really clear relation between the splits graph that are called dark networks and the cycles that they represent. Now, why I'm bringing these, it's because we can use a really similar algorithm like Nanook to implement this identifiability result. So now the input will be a set of sequences that if they were generated under the mixture of coalescent mixtures in an ultrametric network, the output will be the network exactly from the theorem, where you know that you don't get 2 cycles or 3 cycles, and 4 cycles you don't get which one is the hybrid. For bigger cycles, you get all that information. So how this algorithm will work, so given the sequences, using the log to distance and where they lie on the simplex, we will be able to determine for each triplet whether there's a 4 cycle or not, and we'll do for each possible triplet. And then we extend a little bit of some generalization of the Nanook distance when we construct it to create a new distance matrix about that. And then again, we use a splits tree or NeighborNet to construct a splits graph. But now the information of a splits graph will contain a new node. It will be a dark network. The output will be also a dark network, but now with an extra taxon that will be corresponding to the root. And using the same terms to interpret those, we'll get our rooted network. So these are some preliminary things that we're working on. We have the theory about these. I just want to say how much I like splits tree, and this involves a lot of work of Brian, Houston, Dres, Moulton, and a lot of people in this step. It's work on a lot of work by them and others, Kuronabaka, and a lot of people there. And yeah, so what I want to show really quickly is just an example. So we simulated 1,000 gene trees using hybrid lambda. Then we use SeqGen to generate sequences for each gene tree using a GTR model for this network. And we did the algorithm. We just run the algorithm. And this is the actual output from the splits tree, which we can see is a beautiful dark network that we know how to interpret. And this is the actual result after understanding it. And this is exactly what you can see is that network where here is the root. And I think for me, that will be it. I don't know if there are any questions. I'll be happy to address.
Let's thank Hector for the talk. I think Jeremy has a question already in the chat.
Yeah, thanks, Hector. Particularly thanks for such a great explanation of all that stuff. It was really excellent, which is why I have questions. So just a technical thing at the start, when you talked about having a finite set of parameters to sample from, like your finite list, was there a reason for that, why you were talking about, specifically a finite list?
There is, I think this moved, sorry. Yeah, there is in terms of we don't have a way to interpret when you have an infinite number. The limiting case, I don't know if we can work it out.
Okay.
When you have an infinite number. I'm unsure, to be honest.
So it's a technical part of the proof.
Yep.
And is there a reason why GTR and not the general Markov model?
Let me think about that a little bit.
And I have a third question.
Sure.
So once you've done this type of methodology and produced these hybridization networks, is it worth kind of going back, or is it possible to go back and do some kind of likelihood procedure? So in the sense, yeah.
Okay, so that I can address really easily. So yeah, so one advantage of this type of Nanook algorithm, like algorithms, is that they're really quick. They're faster than any likelihood, pseudo likelihood, or Bayesian approach. Yeah, there could be some noise, but I think there could be a really good tool so you can get a starting network and then that fit it to your favorite network method, like even a likelihood. And then when you have a good starting point, maybe it will improve. Something else we really like about a method like this one, like Nanook, is that if you don't get what we call a dark network, that could mean that the hypotheses are not being satisfied, whether your network is not level 1 or there's something going on. Because we know some other methods, they always give you a level 1 network independently if the hypothesis has been satisfied or not. So yeah.
Thank you.
Elizabeth jumped in and answered your second question as well in the chat.
Yep, we have time for one more question. Mohammed, would you like to put your mic on and ask your question yourself?
Sure. Yeah, because okay. So I'm just curious, like, how difficult is it to make a generalization to level 2 network? Since I'm currently doing level 2 network identifiability, but using phylogenetic invariant. But this is just like out of my curiosity. So,
sure.
Thanks.
So in terms of a generalization, what I can tell you and what we have worked so far is that I'm not sure that it will be easy to go from level 1 to level 2. But what I think it can be done is to go from level 1 to something a bit more general. That maybe it's not quite level 2. So in terms of level 2, I'm not sure. I know that there will be some big problems, at least in this case, when you want to go from level 1 to level 2. Yeah. Does that answer your question?
Yeah, thank you.
Okay, great. That's all for now. I'm sure we'll have some more questions in the discussion session at the end. Let's thank Hector again. Our next speaker is David Bryant from the University of Otago. David, I think, is our only speaker who is in a time zone that's ahead of us. Everyone else is behind us by a small or very large amount, but David is 2 hours in front of us, so it's a civilized mid-morning time for him right now. Excellent. Thanks, David.
You're seeing me now, aren't you?
Yes.
Yeah. Right now.
We can see you, David, and the talk. You're in the little box on the window, and we can see the talk in the middle.
Oh, you can see the talk. Excellent.
Yep, all good.
Okay, cool. Well, yesterday we were saying where we are. Yes, in an advanced time zone, I suppose. So it is 10:30 a.m. here, and a sunny Dunedin spring day. I try and show on the camera, but I don't think I'd get the camera back. Okay, so I'm talking this morning. It's really about a project I've been tapping away at for quite a long time, almost 20 years. And with help from collaborators, particularly Daniel Hewson, co-author of the Split History app, along with others, Katie Huber, Vince Moulton, and locally Colin Fox. And the big thing I'm trying to aim for is taking the NeighbourNet method and allowing it to scale up beyond the limit now is probably about a couple of hundred sequences. So beyond that to maybe 1,000 or a few thousand sequences in order to get a visualization of large, or what were considered large data sets. And so the method itself, so NeighbourNet was designed by Vince Moulton and myself probably a good 20 years ago, published a bit after that. And the easiest way to think about it is it's an extension of NeighbourNet to create split networks so that statistically you're kind of overfitting the data, but it allows you to see conflicting signal. And this is a NeighbourNet that I use quite regularly in talks. You have different standard hypotheses being represented in the same NeighbourNet. Now, sometimes sort of coming back to it and working away, we've been trying to make this thing run faster for quite a long time. And I think the number of sort of quite significant and of course now unpublished projects of trying to do the speed up has, there's been quite a history. And in order to sort of jolly myself along sometimes, and also before I talk, I go in and I look and I see it's actually quite cool, because the method is actually being used, and it's that's one thing, but it's being used in the strangest of places. So Google Scholar will let you tell you sort of where a method's been cited in the last few weeks. And so I had a look, and here's a selection of those in the last month or so. And so we have some bacterial, Italian chickens, bats, on bracken, Russian native cattle, magic beans, that's Japanese cypress, leaf curl disease, and this one caught my attention, the Istrian short-haired hound. And as a maths graduate student, I wasn't aware that I'd be contributing to the science of Istrian short-haired hounds. And because you would ask if you could, this is what an Istrian short-haired hound looks like. And so it's for the dog. Right, so NeighbourNet, I don't have enough time today to go through the whole method, but there are 3 general steps. The first, we apply a agglomerative algorithm to get a circular permutation of the taxa. So arranging on a circle, and if you could imagine a tree sitting in the middle of that. So that's the first step. And this is the bit that is closest to neighbor joining. Indeed, we use a lot of the same criteria for neighbor joining. In the second step, we do a non-negative least squares fitting of split weights. And I'm going to talk about that most of the time today, so I'll skip that. And the third step is drawing the actual network. And in this network, the splits are indicated by sets of parallel lines, and we have boxes indicating conflict and so on. It's a generalization of a tree. In terms of computation, this first step takes n-cube time, which is the same complexity as neighbor joining. This last step takes, it depends on the complexity of the network, but it can take up to n to the 4 time. And so that's already limiting by the time you get up to n equals 1,000. And this middle step, solving a non-negative least squares problem, well, I haven't really got a good measure for that because the algorithms we use are iterative. And you know, it's difficult to solve exactly and efficiently. Now, this last step, drawing the network, well, there wasn't much point working on this until we can do the network faster. And last visit that Daniel made earlier this year to New Zealand, not long before lockdown, and we came up with what looks like what you guys are doing in the previous talk, the idea of drawing the outline of the network. And in actual fact, you can reconstruct all of the splits in the network from this outline. So it's a sufficient realization. I think it takes a bit more getting used to. The main thing is that this representation of the splits, or the split network, can be drawn in n² time. So, you know, while we might not choose it for small data sets like this one, when we're starting to have hundreds or thousands of data sets, it's not going to completely stall the computer to draw our actual network. So we're working on this, the least squares problem then. That's the one that remains. That's going to be the bottleneck. And I've tried a whole range of different techniques. But today I'm going to look straight at tackling it from a numerical linear algebraist kind of point of view. Now, this matrix here I wanted to talk about. This is a large matrix, and the rows and columns are indexed by pairs of taxa. And if we consider the distance from, say, taxa 6 to taxa 3, what the matrix scores is which splits separate those. So this split here is separating 6 and 3, so and we have a particular way of indexing that, and so that would get a 1. This split here in green is not separating 6 and 13, so that would get a 0. It's a very similar construction to what you do when you're doing least squares on trees. Now, what we're wanting to do then, given this matrix construction, is we wanted to minimize the norm of AX minus B, or the sum of squares difference equivalently. And it's quite important that we do that minimization with X being non-negative, not only because negative splits don't make any sense, but also because that constraint actually regularizes the problem quite significantly. And the main thing here, computationally, is that A is n choose 2 rows by n choose 2 columns. So if we're doing something like n equals 1,000 taxa, which is quite reasonable to aim for, we're talking about n choose 2 is like 500,000, so it's a 500,000 by 500,000 actually dense matrix. And if you're ever wondering what's going on when the beach ball is spinning during splits tree on your large data set, this matrix has a lot to blame. Okay, so the current method that we do, and this we thought of, Vince and I came up with around about 2004 in time for the MPE publication. We first noted that there's structure in this matrix A we can take advantage of. And we can compute, given any vector, A times a vector, or A transpose times a vector, in n squared time. And that's linear in the number of rows and columns, or rows or columns. So that's as fast as you're going to get. And implement an active set method that's textbook for the least squares problem. There are interior point methods, but they're not actually so useful when we have a solution that's expected to have lots of zeros. So we use an active set method, and what that does is it turns the optimization problem into a sequence of least squares problems that look like this. So for some set of indices, G, or that's pairs, we want to minimize the norm such that the xi equals 0 for every I in that set. Notice we don't have an inequality condition here, and also, I mean, you can write down an analytical solution, but you never would because it's such a big matrix, it would take too long. And we solve this using the conjugate gradient method, taking advantage of the algorithms here for AX and ATX. So that's the current technology, and it's been really quite hard to beat. So the plan method of what we're talking about is to use a replacement of the active set method called a block pivot method, which allows more indices to change from being fixed to not fixed, and solving least squares using what's called a preconditioned conjugate gradient. Now, here's the least squares matrix that you'd solve in order to solve this problem. This is where you get the normal equation. And this notation here is just my dummy notation to say that matrix restricts to indices not in G, like the ones that are active. And you can draw a picture of this matrix where you draw a little dot where there's a non-zero entry and a white dot where there's a zero entry. And you see immediately that this is a dense matrix, and numerically it doesn't give you much to work with. Now instead, what I realized is that you can construct what is essentially called a dual equation to your original least squares one. And now you work with the inverse of A transpose A instead of A transpose A itself. And it happens that A transpose A inverse is very sparse. That's a consequence of the 4-point condition, or at least for circular metrics. So now your big matrix looks like this, and there you see structure, and that is what you numerical algebra ask. That's material to work with. Now I'm not describing an awful lot of dead ends here, but just to say that a very carefully chosen permutation of the rows and columns restructures this matrix. So now we get in this top left, we get a nice sort of 3 diagonals. It's not tridiagonal, it's 3 diagonals because they're not next to each other, and then some sparse matrices. And you can sort of recognize the structure here. So we have tridiagonal matrices here along the middle in yellow. We have sparse matrices in orange next to them. So this is block tridiagonal. And then we have a bunch of green matrices which all merge together, each of which is incredibly sparse. And this is the structure which I've been trying to take advantage of. I thought for a moment that I had an exact algorithm that was going to be super fast, but it didn't work. It wasn't enough. Now, if you're trying to solve a system, we've got a big matrix here, and I've just given these yellow and orange blocks and everything names, A, B, and C. So the first thing you might look at is constructing an LU decomposition, which is what you get with Gaussian elimination. And yes, indeed, it does have a very simple structure, but even with that simple structure, it's still way too expensive. It's like n to the 4 in order to calculate that exactly. And that's just too slow for something that's right in the middle of an algorithm. So instead we look at what's called preconditioning. Instead of solving a matrix equation, say x times something equals y, for preconditioning you multiply it on the left by some matrix M in order to try and simplify. And M has to have the properties that it's invertible, so you get the same solutions, that you can solve equations involving M very easily, and it has to be quick to construct, I should say. I haven't added that list. And then the whole idea is that you convert this equation into one that the conjugate gradient algorithm, which I can't describe in detail, solves quickly. Now we know various things about when the conjugate gradient algorithm works really well, but unfortunately, picking something like a preconditioner is still very much an art, which means, which translates to lots and lots of trial and error and playing around and getting incredibly frustrated. So what I do is I take this LU decomposition of the matrix and I corrupt it. I do approximations, and I want to do as few approximations as I can, because in the end, with my corrupted one, I'm wanting that this LU inverse, which if these were exact would be X inverse. I'm wanting to be as close to X inverse as I can, because that's going to simplify the system. And time constraints means I can't really go into too many of the details. But there was one nut that was particularly hard to crack here. And there was a little problem that if you've got a tridiagonal matrix, so that's got non-zero entries down the diagonal and the diagonal immediately above and immediately below. And it turns out that with linear time pre-processing, you can start querying these entries. Now that plays a key role in being able to officially compute the preconditioner. It's easy to come up with formula using Wikipedia. It's hard to come up with a version of the formula that actually numerically makes sense. Okay, so is it faster? So here's the old algorithm, and this is just for one of the least squares for a very synthetic version of the problem. And we've got error here on a log scale. So here's the preconditioner going on, and we're wanting to get down to like 10 to the minus 10 or 10 to the minus 8 in order to carry on. And here is the preconditioned. Now, in the literature on preconditioners, you grow up to expect preconditioners to sort of come in a very small amount of steps, but this is what it's doing. And so it looks, yes, you're making a remarkable speed up over the original method. But actually, if you extend out a little bit of time, then your precondition is working, and it eventually gets there because it starts improving, and it gets to about 300. So that's like a threefold speed up, which is hardly a justification for what is now about 5 or 6 months of work. You know, there are other things that involve speed ups, but yeah, a little bit annoyed about that. However, this is one example, and what's important is how it scales as n goes, and I have yet to do the coding to get all that working because this is quite fresh. And the other thing is that the part of this line, so this is the error over time, you really want this last thing to be fast, because when you're using the least squares, these calculations are starting from a really crappy estimate of your solution, when actually you can start using the solution from the iteration before and warm start it and hopefully get some advantages. So I spent much of the last 2 weeks translating this code into Java and implementing it in SplitStree 5. Unfortunately, there appear to be only 2 Nexus files on which my code currently works, and there sent me another one which didn't work last night. So that's very much work in progress. Yes, it is frustrating, but after all, we just do it for the dog. So that's me finished, thanks.
And the magic bee.
Thanks very much, David. Jeremy has a question. I'm sure there are more questions, but due to time and the fact that we do have a discussion session at the end, please hold on to your questions, everybody, or type them in the chat if you think you might forget, and we can ask them of David at the end. So our next speaker is Andrew Francis from the Western Sydney University. I need to mention that Andrew has the honour of being the very first registrant, the very first person to register for Philomadia this year. And I thought there might be a bit of duality because, well, it didn't turn out to be perfect duality. He was not the last person to submit an abstract, but he wasn't far away.
Thanks,
David, yeah, I'm sorry. Andrew is going to talk about the case for normal phylogenetic networks. Thank you.
Thanks, everyone. Yep, sorry for being not nearly the latest with my abstract, but it was a very short abstract. It took me a long time to write. So this talk is going to be not very mathematical. It's a bit speculative, a bit philosophical. I'm hoping to just collect a few threads together to make the case that normal networks are really a place that deserve more focus. Not exclusively, of course. There are lots of other things that need thinking about, but there are a number of interesting threads that have come together, I think, that make normal networks something that people should be, I know people are already paying attention to, but a little bit more. So I think some of these things on this first slide you probably don't need to know because you've already seen several network talks, and I know everyone knows that networks are the most important things out there. But I guess basically, just in case you were really wondering, it is the idea, I mean, and there are a number of different manifestations of networks, of course, and Splitstree and NeighborNet are one of them. There's implicit networks that don't, for which the internal vertices are not explicit events. I mean, and I think the first talk this morning was an exception, which was really interesting to see. But I'm going to be talking about explicit networks in which the internal vertices are expected to be representing a real event of some sort. So what I'm talking about in relation to a network is a rooted phylogenetic network. It's going to have a root, which is marked by rho here, and it's going to have leaves, these X's down the bottom. They have in degree 1 and out degree 0. Tree vertices, such as these, have in degree 1 and out degree greater than 1. So if you're a binary person, you'll realize these are not binary networks. So this has got out degree 3 here, for instance, that's a tree vertex. And reticulation vertices, which have in degree more than 1 and out degree 1. So this is a reticulation vertex here, which is in degree 3, and there are a few others around. So trees, this is again probably obvious to everyone. Trees are mathematically significantly simpler. That's not to say that they're simple at all, but they're certainly more constrained than networks. There are lots of models under which they're identifiable, and I'm not going to attempt to summarize those results, but Allman and Rhodes' old paper is an excellent place to start. They can also be reconstructed quite well if you, for instance, have all of the rooted triples on the leaves, then you can reconstruct the network. And again, that's a very old result. Look at that 40 years ago. But there are lots more reconstruction results for trees than there are for networks. Let's not say all the problems are solved. But the networks, a lot of these results have been difficult to come by, but things have been shifting along really nicely recently. So I'm just going to pull together a few stories that focus on normal networks. So it may be confusing. There are so many different families of networks. This figure is one that's adapted from Mike's recent book, just showing a few of the families of networks. So I'm not going to define them all because it's not the sort of thing you do in a short talk, but I will probably mention a few of them. I'll probably just define tree-based networks and tree-child networks. And you've already heard a little bit about level 1 networks this morning. And of course, I'll be talking about normal networks. So trees, of course, sit right here in the middle. Trees are in all of these classes. It's not, trees, I should say, are not the intersection here, but they're a subset of that intersection. So some of these families of networks have sort of more globally structural definitions, and tree-based networks are an example of that. They're ones who have a spanning tree whose leaves are the leaves of a network. So you can think of a tree-based network as one where there's a tree and there are additional arcs between the branches of the tree, between the edges of the tree itself, the base tree. So that's a more global structural definition. The tree-child networks have a more local definition, but they have global properties as well. So they are ones whose internal vertices all have a tree-child, all have a child that is a tree vertex. And the reticulation visible networks over here, which include the tree-child networks, but are included in the tree-based networks, are those for which every reticulation vertex is visible. And I'll tell you what visible is on the next slide. So a vertex is visible if it can be seen from the leaves. I think that's the intuition that you should try to hold. So what does it mean to be seeable from the leaves? It means that there is a leaf on the network for which that vertex is on every path from the root to the leaf. So the one I've highlighted in red here is a visible vertex. There are several in this network. This is the example I had up a bit earlier. So this vertex is visible because there is one leaf, at least one leaf, for which this is on every path from the root to the leaf. So it's not, for instance, this one. This leaf does have this vertex on a path from the root to the leaf. You could come down here and get to the leaf. But there are other paths that avoid that vertex down here, for instance. Likewise, this one, there are paths from the root down to X4, but there are other paths that avoid the red vertex. But X3, every path from the root to X3 goes through this red vertex. So that vertex is visible. So that means somehow that if you're looking at the data at your leaves, that you've got a chance of seeing a signal from that vertex. So tree child networks are those for which every vertex is visible. I said before on the previous slide that reticulation visible networks are those for which every reticulation vertex is visible. Tree child networks have every vertex visible. And that means that and that's basically because if you remember the definition of tree child networks, every internal vertex has a child that one of its children at least is a tree vertex. And if you take a path down through those children, you get a path consisting only of tree vertices to a leaf. And that means that that vertex will have to be, there's no other path that avoids that vertex down to the leaf. So it means every vertex internally is visible in the tree child network. So normal networks are almost tree child networks. I mean, they are tree child networks, but they're almost all the tree child networks, if you like. They're tree child networks without shortcuts. So a shortcut is an edge between two vertices for which there is another path between the two vertices. So that edge there, the UV, would be a shortcut for that other path. So if you take your tree child networks and you eliminate all those that have shortcuts, you've got yourself the normal networks. So just for example, this is that initial example I showed a couple of times already. The visible vertices are shown black. So I think this was the one I highlighted earlier in red. That's a visible vertex. I mean, if you think about it, all of these vertices that are immediately above leaves are going to be visible because there's no way to get from the root to the leaf without going through the immediate ancestor of a leaf. This one I argued for before. That one, similarly, you can't get to this one without going through that one. This one is visible just to that X5 because to get up to the root from X5, you really have to go through there and so on. So you just have to do a little bit of a case-by-case look. Let's look at some of the ones that are not visible. This one is not visible because even though it's below this visible vertex, there is no leaf for which every path has to go through that. In particular, X3 has paths back to the root that go around without going through this vertex here. So that's not a visible vertex. This one is normal. All of these vertices are visible. And I guess to believe that, you probably have to stare at it a little bit. But again, perhaps not too long, because some of these vertices along here are the first vertices above leaves, so they must be visible. So the only ones you really have to think about are these three up here, and it probably doesn't take too long. In fact, it's very straightforward because X1 makes this one visible because it's only got tree vertices up to the root, and X5 makes these two visible. So all of those vertices are visible. Okay, so there are a few nice mathematical properties that normal networks have, and And you only have to have a look at the literature to see papers which prove interesting things about normal networks. Stephen Wilson defined them and proved a lot of very interesting stuff. One result is that every internal tree vertex is a least common ancestor of 2 leaves. So I think that's kind of a profound property, because it means, at least it indicates to me, that every internal vertex has some biological information that's quite specific. It links to specific leaves. This is a beautiful property that I think is in Wilson's paper and also in Paul Curdew, Simona Lintz and Charles Simple's paper. When they were studying networks that display trees more than once. So any tree displayed by a normal network is displayed precisely once. That's quite a strong, neat mathematical result. And it's interesting that these, kind of nice results, I said before that normal networks feel like they're almost all the tree child networks, because you've got all of the tree child ones except those with shortcuts, but those results don't extend. So it's that little property of the shortcuts that seems to mess you up for these results. So some nice mathematical properties for normal networks, and there's also some steps forward in identifiability and reconstruction that I'll mention now. So we've just had a couple of talks, or the first one this morning that mentioned identifiability for level 1 networks. So just my intuitive understanding of identifiability is that your class of networks is identifiable under a particular model if given enough information, a long enough sequence alignment at the leaves. You could theoretically identify the particular network on which the data arose. So you have to think about the model of evolution. So you've got it's a joint distribution. You've got the class of networks and you've got the evolutionary model. So evolutionary models will describe how the nucleotides change along the branches. And on networks, you have to think about what's happening at the reticulations. So how are you constructing your genome alignment as you run down the network at reticulations? So there's a paper that Vincent and I wrote a few years ago. It doesn't mention normal networks. It mentions tree child networks. But we proved that normal networks are identifiable. Well, we proved that tree child networks that do not have a shortcut at the root are identifiable. So that's a little bit larger than normal networks because it excludes only shortcuts at the root, but it does include all the normal networks. So that is the largest complete normal class, usual standard class that is known to be identifiable. There are different, so there's a lot of work going on identifiability for different levels of network. Most models are slightly different to the one we used. So we used a model that was inspired by Balchandra That's paper in 2013, in which, the model we used had the evolution of sequences at reticulations sort of fixed on one of the trees displayed by the network until there was a random change, and then you evolved under a new tree. So your sequence alignment has blocks that were evolved under one tree, and then there's a change to an evolution under another tree, which is a bit different to the usual model of evolution on a network, which might be something like you have a nucleotide that you're evolving at a site, and you come to a reticulation, and you pick a parent for which you choose for the child of the reticulation, and you do that at each site. So at each site along the alignment, you might have a different tree that the site evolved under. So That's model for pedigrees allows us to think of the evolution on the network on one of the trees displayed by the network, and then flip to another, and then flip to another over time. So it's actually got some realism about it, but it's a little bit different to what's commonly studied. Nevertheless, there's an identifiability result for normal networks. And reconstruction, well, networks are hard to reconstruct, and I think like this is the big game. This is the game that David was talking about with NeighbourNet. Well, it sort of that was maybe more representation of relationships. But if you had a method to reconstruct phylogenetic networks from the sequence data, then we'd have crossed some important step, I think, in the use of networks in the biological literature. So networks are hard because unlike trees, even if you have all the display trees, you can't reconstruct a network, and that's Fabio Pardi and Celine Skornovaca's result from 5 years ago. But normal networks can be, at least in the binary case, thanks to Stephen Wilson's result. So that's pretty nice already. Normal networks can be reconstructed from their display trees. And remember, each tree occurs uniquely in a normal network. Each display tree occurs only once, which is kind of a critical property that allows that to happen. But I mean, there's stuff happening all the time. And so this is one of the things that excited me about normal networks, seeing Simona and Charles's paper earlier this year, that you can reconstruct normal networks, at least binary ones, from their sets of triples and four-leaf caterpillars. So, I mean, that's kind of the kind of result I think that is going to bring reconstruction of normal networks, closer to being a normal. Actually, just as an aside, perhaps the name normal would be. It'd be nice to have a different name for this family of networks. It's a word that I want to use all the time, and probably shouldn't. But anyway. Okay. Yeah. So we've got identifiability and we've got reconstructability that are quite strong results, I think, for normal networks. And I think the last property I want to tell you about is a result in a preprint that Daniel Hewson, Mike Steele, and myself put up on the archive a bit earlier this year. It's still under review, but the result is that every network has a canonical normal network. And so you can give me any rooted phylogenetic network, and it has a canonical normal network that represents it. Captures its key information. I think that's probably the way to say it. So the algorithm for constructing this normalized network or normalization is very simple. You take your rooted phylogenetic network, you take its visible vertices, you construct the cover digraph or Hasse diagram, and these were also mentioned yesterday, I think, in Michael Hendrickson's talk. And so the vertices in your cover digraph are just the visible vertices, and you draw an edge between two of them if there's a path between those two vertices in the network, and there's no other shorter path. So you sort of got the minimal cover digraph there. And then you just suppress all the degree 2 vertices that result, and that's your normalization of your network. So what it does is it captures, it's very fast, and Daniel's implemented it with Mike in some software. It's very fast, and I think the idea is that you've by keeping the visible vertices, you've discarded those vertices that you were never going to be able to infer anyway. If your vertices internally on your network are not visible, then the signal is not guaranteed to be in the leaves, and they're not visible. So let me run you through an example. This is that first network I showed you, and there it is. So here is the first step. This is the cover digraph. So let me perhaps, it's still got a degree 2 vertex here, the V9. So let me perhaps point out one of these edges. So this V7, V8 here, there's an edge between them because there's a path from V7 to V8 and there's no other visible vertex on another path, on any path between V7 and V8. And you might say, well, there's a path between V1 and V8, so why don't I have an edge between V1 and V8? And the answer is because there's another path that goes through another visible vertex. So we put that in and we include those edges there instead. So this is the first step. You've got the visible vertices. That's the Hasse diagram of those vertices under the order defined by this path relation. And then you throw away the degree 2 vertex. And that's the normalization of that network. So that's attempting to capture the key information in that previous network. So here's an example that we grabbed from the literature. This is from violets, flowers, not as cute as dogs, but not bad. So this is a paper from Cisbio 5 years ago or so. So that's the relationship among the genus Viola. And then you can construct its normalization, which is significantly simpler. Simplicity, of course, is not necessarily the goal, but and this network, I believe, was constructed using a lot of fossil records and other information. So it's not simply the genetic information at the leaves. So if you were to use the genetic information at the leaves and reconstruct, these vertices are kind of, I think, the most you can hope for. Whereas here, like for instance, just look at this relationship here. There's a posited hybrid vertex there that has a descendant that's sort of, so the information from this vertex could be lost easily along the path here of these other hybridizations, and you won't see it in the leaf. You might see it in the fossil record if you've got access to other. So the key result is that every rooted network has, just by a side remark, since every normal network is also tree-based, it means that every rooted phylogenetic network has a canonical tree-based network. It also has a canonical tree-child network because the normal networks are all tree-child, and a canonical reticulation visible network because normal networks are all reticulation visible, for instance. And there are other neat properties, such as this one. If you take a vertex in your normalization and consider the cluster of leaves below it, it will be the same cluster as the cluster of leaves below the corresponding vertex in the original network. Remember, your vertices in your normalization, your n tilde there, are the visible vertices from your original n. So there is a natural corresponding cluster, and those clusters are preserved. So your normalization is preserving that sort of information. Yep, so to summarize my case, to convince you that normal networks are the way to go, or at least an important, worthy of further work. They've got nice mathematical properties. They're the largest class that's known to be identifiable. They have some of the best reconstructability results. And finally, they do really represent all networks. Every network, every rooted phylogenetic network has a unique canonical corresponding normal network. So my feeling is that they are the sweet spot, because if your data evolved from a process on a network, then your normalization is the most information you can reasonably hope to obtain, because you can't really hope to get more than the visible vertices. But it's also the most that can practically be obtained, because there's no other way to capture that other information, well, except adding additional data, I might say. And so I'll end there, and thanks to the three collaborators I mentioned in today's talk, Mike, Daniel, and Vincent, and there are some key references. Thanks.
Do we have a question or two for Andrew? Well, we might go straight into the discussion session then. Oh no, we have a
If you've got
question.
time?
Yes,
Just a
definitely.
quick one.
We have a question from
For
Mike.
Andrew. You don't like the term normal. What else would you call it?
You know, I haven't. I guess I haven't really tried to come up with a name. It'd be a bit impolite to change the name. You know, somebody came up with that name, and I just yeah, it's a tough one. I mean, I feel like something to do with visibility would be good.
Sure.
Have you got a suggestion?
Not yet.
Okay, let's thank Andrew again. I do think that normality, the word normal, is overused in mathematics. I mean, every second thing is normal, which, you know, it's not actually.
Well, that's my feeling too, Veta. I mean, you know, it's not a normal subgroup. In what sense is it really normal? It is canonical, as I've been claiming. Yeah, I think it's overused not only in mathematics but overused everywhere. You know, so anyway, it is what it is. That's the way language comes.
Yes. Okay, so let's thank all of the speakers so far in the session for some excellent interesting talks. And I would like to introduce our people who have done pre-recorded talks for the discussion session. So that is Katarina Huber, Vincent Moulton, and Yukihiro Murakami. I'd like to thank them all for coming. I haven't seen Yukihiro at such a late time for you, and I really apologize for the confusion with the scheduling. We'll work on that if we have to do another online conference, that we present the format of the discussion sessions a bit more clearly in the program for everybody. But thanks so much for coming. If anybody or other people would like to turn on their cameras, we can make it feel a bit more friendly. But would Vincent and Kati, would you like to just briefly tell us about the contents of your talks?
Can you hear me?
Yes.
By context, what do you mean exactly?
Content? Or maybe if you could do an executive summary, or, you know, maybe one or two main results, or what you'd like to tell us that was in your talk.
So, well, I think basically speaking, if you have an unrooted phylogenetic tree, you can look at the with weights, you can look at the distances on there, and you can reconstruct the tree uniquely from its distances. So in my talk, I was interested when you have an unrooted phylogenetic network, but first, without weights, when can you reconstruct it back from the distances between its leaves? And we were able to show with Yuki and Leo that you can always build back a level 1 network. So you basically have very simple network there. You can always build that back, but you can't build back a level 2 network, for example. But then you can look at multi-sets of distances, and you can then still build back level 2, but then you can't then build back level 3, even from multi-set distances. And we also looked at some extension of that with Yuki and Momoko and Kati, where we looked at weighted networks, and you can build back weighted level 1 networks uniquely, but you can't build back level 2. And level 2 is even more unpleasant if you have weightings, because you can have infinitely many networks with the same distance. So sort of, it's kind of work in progress, but I think, you know, obviously the main game, as Dave and Andrew have already mentioned, is eventually we ought to be trying to build back networks from real, you know, from real data. And I've always taken the philosophy a bit that if we don't really understand how to even build back networks from perfect data, then how can we really come up with these algorithms to build it from real data? But at some point, you know, I think we're still a little bit, well, other than what David's been doing, and of course what we've seen from our earlier speaker, where we have these nice results now from these trinets or triplet networks. You know, we need to try and now start to forge ahead and get some algorithms that actually build back networks from real data. So anyway, that's a little summary of my talk.
Excellent, thank
Yep.
you. Jeremy has a question.
Can I ask a question? So sorry, Vincent, that it's just a yes or no. But with the result, is it just that, do you have to know that it's a level 1 network to see that?
Yes. I think yes, basically. You mean we know we've got the distance from a level 1. So, I mean, if we want to decide whether a distance matrix comes from level 1, level 2, etc., then I don't think we know that answer to that. But maybe Yuki or Leo can comment on that.
Maybe I can say something on this. So if you have a level 1 network and, well, you generally start with the distance matrix, and if you just assume that the distance matrix represents the shortest distance of some network, then you can just apply the steps that we showed in our paper. And if a network pops out, then you have a level 1 network. Otherwise, you probably have a network that's a bit more complicated, so with a higher level. So you don't need to know if the distance matrix belongs to a level 1 network before you apply the algorithm to it.
So it's not possible to get a distance matrix from a level 2 network and apply the method and get an answer which is a level 1 network?
No, it's not possible.
Kati, would you like to give us an overview of your talk?
Yeah, I can. I mean, my overview is probably much shorter than Vincent's. Now, in my talk, I'm reporting on the question we have been looking at recently with Simone Linz, myself, and Vincent, namely, how do I display trees in the network? And usually people display trees in the network in such a way that they see the tree, they obtain the tree from the network by just deleting incoming edges from hybrid vertices and then suppress degree 2 vertices. Now, the point is that every edge in that network displays an edge in the tree at most once. So what happens if I allow more than one edge in the tree to go through the same edge in the network? So I have a network, an arc in the network, I should say arc, not edge, and two different edges in my tree go via this edge to the leaves. Now this is what has been introduced as weakly displayed, and weakly displayed is related to these weak embeddings that Leo and co-workers introduced. And the question becomes, under what circumstances is actually this displaying, which is the standard way of seeing trees in networks, is the same as this more loose way of displaying trees in network, this weakly displaying. And that's what my talk is about.
Great, thanks. Do we have some questions? I actually watched your talk yesterday evening, and I had a question. I watched Yuki's talk, and I was like, that's cool, I understand cherry picking. And then you talked about fork picking, and I really wanted to know what that was, but perhaps I should just read the paper. I'm not sure. Is it easy to explain?
It is relatively easy to explain. So you have two trees on the same leaf set, and suppose you have two cherries, and in a cherry X, Y in one tree and a cherry X set in the other tree, then you can remove the X in both trees and therefore get a smaller tree from the first one and also from the second one. And if you can pick up all the cherries from your two trees in this way, then you have a cherry picking sequence.
But I think the question was, what's the difference between cherry picking and fork picking?
the for-picking sequence is a generalization of the cherry-picking sequence, and it has three. So in the cherry-picking sequence, you're only looking at cherries of trees. In the fork-picking sequence, you're looking at 3 forks, which is triplets and 4-leaf trees, rooted trees.
Okay,
And
so 3 and 4.
3 and 4. So you're generalizing, and we know that every fork-picking sequence can be translated into a cherry-picking sequence, and I think the other way around too. But it's more complicated because you have to be able to control what happens with regards to what happens if 2 edges from the same tree go through the same arc in the network.
Sure. Yuki, would you like to summarize your talk for us?
Yeah, of course. So this was joint work with Remy Janse, and basically what the question that we looked at was the question of network containment. It's given 2 networks, N and N prime. The question is, can you decide whether N prime is contained in N? And there, by contain, we mean exactly just what Kathy said there, by an N displaying N prime. So can you obtain this network N prime by deleting a few reticulation edges and suppressing degree 2 vertices from N? And this problem, as it turns out, is NP hard because the easier problem of deciding whether a tree is contained in a network is already hard. So what we looked at was we said, all right, so let's just look at tree child networks, which is what Andrew mentioned in his previous talk. And we said, right, we have 2 tree child networks. Can we decide whether one is contained in the other? And to solve this problem, what we did was we introduced a few graph operations. It's quite commonly seen within phylogenetics, and we called them cherry picking. So we picked on 2 leaves. If 2 leaves have a common parent, then they form a cherry. If 2 leaves have 2 parents where one parent is a parent of the other, and that parent is a reticulation, then you could sort of call that a reticulated cherry, and you could define operations on them. And with these operations, you obtain a sequence of ordered pairs on the leaves. And what we showed was that N prime is contained in N if and only if any sequence that reduces N, which is the larger network, reduces the smaller network N prime. And we showed that for the tree child networks. And what I can also say is that the theoretical running time for deciding this problem is linear. And we had a bachelor's student, Robert Hausman, implement this in Python. And in practice, it was also running quite quickly in linear time.
That's great. I actually had a question as well. So you said at the end of your talk that you extended to non-binary networks.
Yeah.
So did you still obtain linear time for the non-binary ones?
So for the tree child stuff, for the non-binary, what we meant there was that, so for the tree vertices, we still need the out degree to be 2. So for tree vertices, you need that the degree of the vertex is exactly 3. And for the reticulations, you can have as many reticulations coming in. And for that particular class of networks, then the linear time still holds. But if I remember correctly, the result for a reduction implying containment and containment, or I think it's containment implying reduction, doesn't actually hold if you start having non-binary tree vertices.
Okay. Great, thanks. Are there further questions for Yuki? Or Vincent or Katerina? Or for any of our speakers from earlier in the session? Jeremy, you were waving your hand around, I think, after David's talk.
David and I have had some private discussions.
Aha. Yes?
I have another question for Andrew, if I can just pull it up. Hang on.
Yes, maybe speak up a bit so the tracking
Yeah, I will.
camera finds you.
Hello. Okay, so another question for Andrew. You said you've got the largest, you think it's the largest set of networks that have this wonderful property that every internal, what was it? You think it's the maximal size that are identifiable, or it's known to be identifiable?
Yeah, I mean, we don't.
Do you have a gut feeling as to whether it really is the biggest, or how you might go about finding that out?
So Vincent and I proved that the class of tree child networks for which there's no shortcut at the root are identifiable under the model that we used. And so I mean, my feeling is, and Vincent may have a thought on this too, is that I don't think you can get any bigger than that, because we really depended on a lot of the properties of tree child networks to get that result. However, identifiability is a function of the model, the evolutionary model that you're looking at. And one of the reasons we were able to prove identifiability for quite a large class, that almost all tree child networks, is because we looked at a different model to what people sometimes look at, which is that site-based model of evolution. We looked at a block-based one where the tree that the alignment evolves on is sort of more or less constant, and there's a certain probability it changes as a tree at a certain point, and so it changes to a new tree. So the thing is that model gives you more power than the other one. I guess that's the conclusion of what Vincent and I did. But there may be other models that are out there under which larger classes are identifiable, and that's something I don't know, and I don't also know, like I mean, I think the model we used is actually quite realistic, because if you have a hybridization, or if you have a horizontal gene transfer event, you do get a block of DNA usually that is coming from a different tree. So your alignment should have blocks like that. So I think it's reasonably realistic. But maybe there are other models that I don't know about. There's certainly many that I don't know about. Maybe there are other ones that are more realistic, or carry different information and under which identifiability is possible to be shown. So does that answer your question, Mike?
Yeah, it does. Yeah, thank you.
Do we have any further questions? I'm not seeing anything in the chat. I guess people have been doing separate chats. But if there is nothing else, then I will let our European and English friends go to bed. Thanks, everybody. And we will reconvene in approximately 45 minutes. 42 minutes at 10:15 Tasmanian time. Thanks very much.
Stretch legs.